All right, let's switch gears from strong acids and bases to weak acids and bases. A weak acid it is not the same as a dilute solution of a strong acid. The reason why I say that is, let's say you have a dilute solution of HCl. So a concentrated solution would mean something like 1 molar. A dilute solution A dilute solution would mean something like maybe 1 times 10 to the power of negative 4 molar. Okay, and if you say I want to find out the pH of the solution, so you would say, well, the acid is strong, it's HCl, and so negative log of 1 times 10 to the negative 4, which comes out to be 4. pH is 4.0. Right. On the other hand, if this pH of 4 was or had to be achieved by a weak acid, its concentration will be very different and the way it will ionize will be very different. So a strong acid, realize, is 100% dissociated in an aqueous solution, whereas a weak acid is only partially dissociated. What that means is that if you had, let's say, 100 parts, out of those 100 parts, maybe only 17 do. Okay, so it's only partially dissociated, and that can be illustrated using a picture. So let me draw something for you real quick. Let's say you have HCl plus H2O giving you hydronium and Cl negative, right? And if you want to show like a picture of it, you have water in here, okay? And you dropped, I'm going to put maybe like a solid sphere for Cl, and as it hits water, when it reacts with water, you're going to end up with Cl negative, Cl negative, Cl negative, Cl negative. So you can see that the H plus has added on to the H2O to give you the hydronium. So together they're forming the hydronium ion. And for every chloride, there is a hydronium ion. And if there were like 4 molecules, all of them have been split. Also notice in this case that I have a single arrow. Single arrow denotes that the backward reaction is minimal, and hence it's a complete ionization that we are talking about. So if you consider an HCl solution containing virtually containing, let's say, 1 times 10 to the negative 2 moles per liter, then virtually there is no intact HCl. The HCl is essentially all ionized to form hydronium ion and chloride with a complete dissociation, as I showed you in this picture. So 1 molar or 1 times 10 to the negative 2 molar solution will have hydronium concentration of 1 times 10 to the negative 2. So if you start with 1 molar, this will be 1 and this will be 1 as well. If you start with 1 times 10 to the negative 2, this will be the same. So the original concentration of a strong acid remains the same. You can determine that immediately very effectively. This is for strong acids. Strong acids. What about weak acids? Let's say something like HF plus H2O gives you H3O plus F negative. First thing you should notice is use of the equilibrium. That means there is a forward reaction, there is a backward reaction, or a significant backward reaction. What that means is if you drop HF in to water, essentially you will have water. Maybe one of those is going to or water was blue, right? My bad. So you will have water. Majority of it is as is. One of it has picked up the H plus to form the hydronium ion, and maybe there would be one fluoride, and I'm putting in a smaller solid sphere to denote the F negative. So the equilibrium arrow, like I said, shows partial dissociation. So if you had an HF solution containing a large number of intact or unionized HF molecules, and it will contain some hydronium ions and it will contain some F negative. In other words, 1 molar HF solution has hydronium ion which is much less than 1 molar. So the concentration of hydronium in this case is going to be much lesser than the initial concentration of the HF, because most of it is going to remain undissociated. Only some of those are going to form the hydronium ions. Now, the degree to which an acid is strong or weak depends on the attraction of the anion of the acid, that is the conjugate base, and the hydrogen ion. That means how well it's going to ionize really depends on how well the F and H are bonded to each other. If you can break that bond, then of course, the acid is going to be considered strong. On the other hand, if it's a good overlap, then you will not be able to break the bond, and you will consider that to be a weak acid in that case. And so the degree to which a reaction takes place in terms of the forward reaction obviously depends on the attraction of the H plus with the corresponding conjugate base in this case. So you can perhaps envision that in case of HF, the bonding between hydrogen and fluorine is going to be pretty strong, since the orbital overlap is pretty good due to similar energies. That bond will not break very easily. That means F negative has an attraction towards the H plus. On the other hand, the Cl does not, and so HCl is going to be a stronger acid as compared to HF. Now, just to make sure everybody's on board, stronger is the acid. Stronger acid implies weaker conjugate base. Weaker conjugate base. I said that in the previous video also, then I say that again, so must be an important point. What that means is that if the forward reaction of the acid that has a tendency to occur, then the backward reaction will have a lower tendency to take place. So what that means is if you have a strong acid like HCl, realize you have a complete single arrow. That means the backward is going to be pretty small or will not occur at all. Anyway, now there are monoprotic acid or monobasic acids, and they are also what are called as polyprotic acids. So if you see something like HF, which has only one hydrogen to lose, we will use the word monobasic or monoprotic. Monoprotic. Likewise, if you have acetic acid, CH3, COOH, there's only one H that gets lost, we use the word monoprotic. On the other hand, if you have sulfuric acid, sulfurous acid, both of these are supposed to be lost, we use the word diprotic. Likewise, if you have a moderately strong phosphoric acid, 3 of those have to be lost, we are going to use the word triprotic, so on and so forth. Okay, now let's take a look at what happens as a weak acid is put in water. Basically, the dissociation of the weak acid, when you put it in water, it can be characterized by this equation. I have a general equation, general formula HA plus water, and that's an equilibrium to give you hydronium plus A negative. So one can say that basically HA has undergone dissociation to give you the proton and the A minus. If you had to write down the equilibrium constant for this reaction. You would say, well, K should be equal to hydronium ion times A negative divided by HA. You do not include water because it's a liquid. That's right. This K has a specific name. It's called as the acid dissociation constant, and the value of Ka is going to tell us how well the dissociation has taken place. So although for all ionization constants, for all weak acids, these are relatively small, but they do vary in magnitude. And so smaller the constant, smaller the value of K, smaller is the value of Ka. That means weaker will be the acid. Weaker is the acid. Or larger Ka means stronger the acid. So for example, if you compare HClO2, which has a Ka value of 1.1 times 10 to the negative 6, or negative 2, my bad. And let's say I have another one, formic acid, HCHO2, the Ka of that is 1.8 times 10 to the negative 4. Which one do you think is a stronger weak acid? The first one, because the Ka is a larger number as compared to formic acid. All right. If you take the negative logarithm of this value, that means if you try to determine pKa, realize you're going to get a smaller number. And while we're at it, let's actually work out the math. And the pKa value on my calculator came out to be 1.95 for HClO2. If I take the negative log of the other number, so that will be 0.018, and I take the log, that comes out to be 3.74. So could I say that stronger acids have lower pKa's, right? So lower pKa implies stronger acid. These two things are pretty important for those of you who have to take organic chemistry or plan to make a career in pharmacy. So low pKa, stronger acid, which basically means the Ka would have been larger. Just out of curiosity, I'm curious if you can put things in perspective. If we just determined that HClO2 pKa was 1.95 and it was a stronger acid than formic acid, which has a pKa of 3.74, so that was the weaker acid. What can you comment about the basic strength of ClO2 and formate? Anybody? Well, hopefully you are thinking, as I am thinking, stronger is the acid, weaker will be the base. So this guy is going to be weaker as compared to formate. All right, let's take a look how we can mathematically figure out the pH of solutions of weak acids. Realize we cannot just use the concentration, the initial concentration, because it is an equilibrium. So we will have to determine the concentration at equilibrium and take it from there. Okay. Just to kind of give you an example, just to give you a flavor of this. If you take 0.1 molar HCl and you measure the pH of that in the lab, it'll come out to be 1.00. If you take the pKa, or I'm sorry, the pH, both of these are pH, the pH of 0.1 molar acetic acid, and you measure the pH of that comes out to be 2.87. Okay, so the pH of acetic acid solution is higher as compared to, so the pH is higher for acetic acid. It's higher than the pH of HCl. And that makes sense because acetic acid is a weaker acid as compared to HCl. And in order to do the calculation as to how to go about it, you can't quite just take the initial concentration of acetic acid as is. You have to actually work through a certain level of math. So we'll do that using HCN. The question is, calculate the pH and the concentration of all species present in 0.10 molar HCN. Now, Ka is provided to us. We, of course, have a general equation of ionization that hydrocyanic acid reacts with water to give you hydronium ion and cyanide. So that's my general reaction. And I can say that Ka is hydronium ion times cyanide divided by HCN. And this number, the numerical value, has been provided to us. Now, realize if I have to determine the value of pH, pH by definition is negative logarithm of hydronium ion. So I will have to figure out the concentration of hydronium ion. Since this is a balanced equation, stoichiometrically I can say that 1 mole of HCN reacts with a mole of water to give you a mole of hydronium and cyanide. So whatever is the concentration of hydronium, same should be the concentration of the cyanide. These problems are best solved by what are called as ice problems. So I'm going to write down the equation again. HCN plus H2O gives you hydronium plus Cn negative. We discussed the ice problems in chapter 14 as well, the initial, change, and equilibrium. My initial concentration for HCN was 0.1 molar. Of course, there won't be, water is not going to contribute. There won't be any hydronium or cyanide in the beginning of the reaction. And let's say that only X moles essentially participated in the reaction. What that would mean is that X moles of hydronium and X of cyanide would get generated. And so you're going to end up at equilibrium. So the way we figured out equilibrium was that you simply add the initial and the change. This is the initial, this is the change. And so you would say it's 0.1 minus X. This is X, and that is X as well. And what that would tell you is that if you have your Ka set up, it's going to be X times X divided by 0.1 minus X, and that value has been given to be equal to 4.9 times 10 to the power of negative 10. Now, X squared is 0.1 minus X, 4.9 times 10 to the power of negative 10. If you try to solve this, you might think that this will end up being a quadratic equation, and yes, in some cases you might have to actually solve that as well. But it's always good to look for the approximation, whether the approximation holds true or not. And the approximation is that you take the ratio of whatever is the value of X that you have. If the X is, because realize this X, this ionization is very, very tiny. So if there's two ways to look at it. If your initial concentration divided by the Ka value, so the extent that it dissociates, if that value is more than 100, then you can use the approximation. If it's not, then you cannot use the approximation. Another way to view this is that you basically confirm that x is small and so small by looking at the ratio of x to the number it was subtracted from in the approximation, and that ratio should be less than 0.05. So there's two ways to look at it, and I'll show you how. So initial concentration, in this case, both of them, they mean the same thing, but just to make sure. So initial concentration is 0.1, Ka is 4.9 times 10 to the negative 10, and when you work that out, it's going to be like 10 raised to the power of 10, which is going to be way more than 100. So yes, approximation is applicable. And so we are going to assume that x is going to be small. X is small. That means 0.1 minus x is going to be approximately equal to 0.1, or one can say that x squared is equal to 49 times 10 to the power of minus 12, or x is equal to square root of 49 times 10 to the power of minus 12, which is equal to 7 times 10 to the power of minus 6, 7.0 times 10 to the power of minus 6 molar. And if you wanted to check the approximation one more time, this is the value of x that we just obtained. So let's check that as well. 7 times 10 to the power of minus 6 divided by 0.1. So that was the original concentration times 100. And that came out to be 7 times 10 to the negative 3%. It's supposed to be less than 0.05. So yes, the approximation is valid. One way or another means the same thing. If this is X, that means this is hydronium as well as cyanide. So what would be the third species? HCN is the third species, right? And so what you can do is you can simply subtract this number, 7 times 10 to the negative 6, from 0.1 to get the answer for HCN. In order to determine the pH, what would you do? Since you already have the hydronium ion, you will just take the negative log of 7 times 10 to the negative 6, and that will give you the pH. And on my calculator, the pH is coming out to be 5.15, and the subtraction is going to be 0.099993 molar solution. Now there could be some situations where the approximation doesn't work. Approximation doesn't work. What do you do then? You still have to determine the pH. Well, in that case, you will have to solve the quadratic. As an example, I have here HF with water gives you H3O plus F negative. And I have, the question is, calculate the pH and concentration of all species, these three species, when concentration is provided, Ka is provided. So again, you're going to write down the expression of Ka, that is going to be hydronium times F negative divided by HF, and that is equal to Ka. So 6.8 times 10 to the negative 4 is equal to, let's write it in the format of an ICE, so that will be 0.05, 0 and 0. This is going to be minus x for the change, C is for change, and E is for equilibrium. So x 0.05 minus x, and that's going to look like x times x divided by 0.05 minus x, and let's solve that. So x squared divided by 0.05 minus x equals 6.8 times 10 to the negative 4, And if the question is, now if you have to ask whether the approximation holds true or not, you're going to take a look at the concentration, 0.05, 0.05 divided by the Ka number. And when you try to find out the ratio, that comes out to be like 70.05 divided by 68, 73.5. So that value is not more than 100. You cannot use the approximation. So in this case, you will have to solve the quadratic equation. I've given you the solutions. If the equation is ax squared plus bx plus c, so substitute that and solve for the two value of x. The only one thing I would suggest is a negative number cannot be a concentration, so you can simply ignore that particular answer. For your dry lab, there is one or two questions that require you to do this. Everything else you will probably be able to solve without having to worry about the actual quadratic, so you would be able to use the approximation directly. But always show your work, always show that yes, whether or not you know how to figure out whether you can use the approximation or not. Okay, let's talk about the percentage dissociation, which is basically the amount of acid dissociated divided by the initial concentration times 100. Higher is this value for the percentage dissociation, stronger is the acid. And this usually will increase as the value of Ka increases, and of course it also increases as we start to dilute the acid. So weak acids in general will have a tendency to remain coordinated, which is why their percentage dissociation can be lesser. So let's discuss polyprotic acids. Acids that contain more than one dissociable proton, and I showed you the diprotic and the triprotic acids. Realize that the dissociation, one way or the other, the dissociation is going to occur in a stepwise manner. So essentially, each dissociation will have its own Ka value. The first dissociation usually will be larger. So, like the example that I gave you for sulfuric acid, the first dissociation is responsible for the entire amount of hydronium ion concentration. The second one is just an equilibrium reaction. One can safely say that the first ionization is going to be stronger than the second, than the third, so it's going to be obviously more difficult to take away a proton from an already electron-rich negatively charged species which doesn't contain as many protons in the first place. I think what I'm going to do is just basically provide you more examples of some ice problems so you can see and put things in perspective, and we'll move over to the bases thereafter. So I made a couple of statements. I said that the degree of ionization, usually given by alpha, that increases as concentration of the weak acids as that decreases, that means we have more dilute solutions, we see a better degree of ionization. So I want to give you a mathematical example for that. So the question is that we have to determine alpha for the percent ionization. In other words, for 2.5 molar HNO2, when the Ka of that is given to be 4.6 times 10 to the negative 4. That's the value of Ka. Okay, so you would say, well, your reaction is HNO2 plus H2O gives you hydronium plus NO2 negative, right? And so for the ice, you would say that this will be 2.5, 0, and 0. This will be minus x. This will be plus x. That's plus X also. Reason why we write it like that is because for every mole of HNO2 that undergoes dissociation, the same number of moles of hydronium and nitrite are going to get generated. Equilibrium is just the summation of the two. So that's what we have. So I say Ka is equal to hydronium, which is X, times nitrite, which is also X, divided by HNO2, which is 2.5 minus X. And so when you plug in the numbers, looks like it's going to be X squared upon 2.5 minus X is equal to 4.6 times 10 to the negative 4. And when you try to look for the approximation, concentration is 2.5 and the value of Ka is 2 point is not 2.4 point 4.6 times 10 to the negative 4. That's to the tune of 5434.78, way higher than 100. So we can apply the approximation. So I would say that X is much smaller than 2.5 minus X. And so we can say X squared divided by 2.5 is equal to 4.6 times 10 to the power of negative 4. So we are going to try to solve this. X comes out to be equal to 0.034 molar. And if you have to calculate the percentage ionization, that will be the value of hydronium at equilibrium. So 0.034 divided by what you began with times 100. And this value comes out to be 1.4%. I want to do the exact same thing, but now at a lower concentration, let's say 0.2 molar. Everything else remains the same other than the initial concentration. So your Ka will look like X times X divided by 0.2 minus X, because my 2.5 is going to be switched with 0.2. So now I have X squared 0.2 minus X is 4.6 times 10 to the negative 4. You would be able to use the approximation. So X is much less than 0.2. And that would mean this boils down to X squared divided by 0.2. 4.6 minus 4.6 times 10 to the negative 4. And we will solve for X. And it comes out to be 0.0096. X comes out to be 0.096. When I calculate the alpha or the percentage ionization for this, it'll be 0.0096 divided by 0.2 times 100, which comes out to be 4.5, approximately 4.5, 4.8 rather percent. So realize dilute solutions, better ionization, more amount of hydronium ion if the acid is weak.